Okay, before we get started, I should apologize for my squeaky chair. You're going to be hearing my squeaky chair throughout my discussion here. Hopefully it won't be too bothersome here. We're going to be talking about something interesting today. It sounds like a haunted house behind me here. We're going to be talking about something called Poincare classification. And Poincare classification is a way of classifying the origin as an equilibrium solution. And so let's see how we would do that. So we're solving x prime equals ax, which means that we have our characteristic equation, which is lambda squared minus the trace of a times lambda plus the determinant of a equals 0. And then if we solve using the quadratic formula, right, we get that lambda is equal to the trace of a plus or minus the square root of the trace of a squared minus 4 times the determinant of a, all divided by 2. Good. All right. And then let's see, we define the discriminant, delta, to be our trace of a squared minus 4 times the determinant of a. Okay, and so the solutions depend on the discriminant, right, from our quadratic formula. And just to run through what that is, if lambda equal, or if delta is greater than 0, we get 2 real evals, right? Discriminant equals 0. We have 1 double real eval. And if the discriminant is negative, we get complex evals. So we see here that the discriminant kind of separates our two types, our real and imaginary parts. So it seems like that's kind of an important separation. And so if we look at where delta equals 0, that's the dividing line, so to speak, then that's where the trace of a squared minus 4 times the determinant of a equals 0. Good. Now, if I think about the trace as if it were the x-axis and the determinant as if it were the y-axis, then this equation becomes x squared minus 4y equals 0, right? I'm going to put quotes around that. Or y equals 4x, 1/4 x, sorry, squared, 1/4 x squared. And so I could draw the parabola in the trace-determinant plane, and on the line, or on the curve there, is where the discriminant is equal to 0. Good. And so this is very interesting, because now we can kind of track the behavior of our solutions, or really the classification of the origin based on the trace and the determinant and the discriminant. Okay, and let's see how that's going to work, because now I'll redraw this a little bit bigger. Before we do that, let's get familiarized with this plane. So this curve, where discriminant equals 0, separates the plane into two pieces. One of those pieces is inside the parabola, one piece is outside the parabola. One of those corresponds to the discriminant being positive, and one of those is where the discriminant is negative. I wonder which is which. So here's a way to check. How about this point right here? In that case, remember our discriminant is trace squared minus 4 times the determinant of a. So if I put in this point, what does that correspond to? That corresponds to the trace of a being 0 and the determinant being positive. And so what happens here then is the discriminant is negative, right? So inside the parabola is going to be negative discriminant, and outside the parabola is going to be positive discriminant. Good. And so let's find some other places in the determinant trace plane that we can take a look at. Oops. Okay. That's not supposed to be so linear. Okay, so trace of A, determinant of A. And let's suppose now that I've got any point down here in region A. Call that region A. So what is distinguishing about region A is really the trace is changing from positive to negative, could be 0. What's really here, what's happening in region A is that the determinant of A is less than 0. And I wonder why that's important. Well, if we remember our lambdas, they are where the trace of A plus or minus the square root, trace of A squared minus 4 times the determinant of A. What happens to my expression in here? Maybe I should get a different color. What happens to my expression in here if the determinant is negative? Well, if the determinant is negative, that means that this expression in the box here is bigger than the trace of A squared. And so therefore the square root of this quantity is going to be larger. This is going to be larger than the trace of A when I take the square root. So what does that mean? That means, whoops, that if the trace of A is positive, right, then we're going, if the trace of A is greater than 0, then lambda 1 and 2 will have different signs. And similarly, if the trace of A is less than 0, do we get different signs again? Yes, because this positive part, right, will mean that, lambda, one of the lambdas is going to be positive. So the same thing happens. Okay, and so what happens? So the summary of what's happening here is that down in this region we get saddles. Okay, so we'll go through here and maybe check out a few of the notes, go through a couple more places here, but just to fill in some more of these regions, if we're in this region here, we end up with sources, and in this region we have a spiral source, and in this region we'll have spiral sinks. Oops. If we hit the curve, we end up with a degenerate sink. Or if we hit this curve, we get a degenerate source. And then if we hit this one, we get a center. Okay, so this seems like it's an awful lot to keep track of. And therefore, we're going to use the Poincare classification diagram. And I will allow you to use that for any of the exams coming up. So it's a good idea to just familiarize yourself with that. It's on our class website, and it's a better version of what you're looking at here. It's a lot nicer. Okay, so I think I'm going to stop there for now. I've got another example that we're going to use the Poincare classification diagram for, but we're running out of time for this video. So see you in the next video.